Okay, we are in Advanced Math Trig Honors, Mods 2, 3, and 4. Today is Tuesday, 4/21/20, so top left corner of your paper. Today's date, 4/21/20. If you remember yesterday on Monday, we finished up our logarithmic equations. We got through all 20 of those on that worksheet. And to end this exponential / logarithmic chapter, one of the most famous formulas that, yes, you'll use a lot in calculus next year and is always introduced at this level, is our exponential growth and decay formula. Now, even though the title says exponential growth and decay, almost indicating that we should see two formulas on our paper, that's not true. We've got a growth formula called y equals b times e to the kt power. And that formula is used whether something's growing or decaying exponentially. The only difference between the two is if it's a growth problem where something's growing and multiplying and getting bigger and bigger at an exponential rate, the k, which is going to be the rate that something's growing, will be positive. If it's a situation where I've got material that's decaying and it's weighing less and less and less, then we still use the same formula. It's just that our k value, our rate formula, is going to end up being a negative value. So, top of your paper, 4/21/20, Tuesday the 21st. Exponential growth and decay is your title. Put a big star in a box around our key formula of the day. And you'll actually use this a lot next year in calculus when you start doing differentiation and even integration of things. So be familiar with it. It's a great day to go over this at the end of this chapter we've been working on, because notice it's an equation with missing exponents, and we're going to utilize some of the skills we've learned up to this point. What do all those letters mean? We're just going to make a little note on that. It is in function form where it says y equals, because it is an exponential growth and decay function. Y is going to end up being the final amount of material that's present at a certain time, or at the end of an experiment, so to speak. So whether something's growing like a bacteria or a virus or population or a bank account, anything that's growing at an exponential rate, y is going to be our final amount of material. And when you look on the other side of the equal, I'm using the letter b because b is the beginning amount, or as they define in our book, the original amount of material. So b is what's there at the beginning. Y is going to be the amount there at the end. Okay, final amount equals beginning amount times, of course, we're familiar with the letter E, raised to the kt power, where k is the rate at which something is growing. Again, that'll be a positive value if it's getting bigger, a negative value if it's getting smaller. And t, of course, is the amount of time that that stuff has been allowed to grow or get bigger or smaller. Okay? So with that formula in mind and being familiar now with what all the letters stand for, let's look at our first problem. So put now. Let's just say that, I don't know, you go to the doctor and you think maybe I've got strep throat, and so they swab your throat and have a material available. I'm just going to make up numbers here, but let's say there's 2,000 milligrams of something that's sitting here, and we're going to let it sit for 6 hours. And at the end of 6 hours, that 2,000 milligrams of material is now grown and multiplied and generated and kept getting bigger and bigger, and is now 6,000 milligrams. So something's, again, I'm just picking nice, neat, easy to work with numbers here to prove how this formula works mathematically. So now we've got 2,000 milligrams. That's our original amount. We're going to let it sit for 6 hours. At the end of 6 hours, it's grown to 6,000 milligrams. So I want to know, what's the rate with which it's growing? What's the growth rate of that material? Now, careful, it's not as simple as saying, oh, well, it was 2,000 and now it's 6,000. It's tripled in size. And, throw a number down like 300% growth. Okay, I don't want to know how much it grew total. We want to know the growth rate. Anytime you see the word rate, it's what? So much per hour. So it might be growing at a rate, I'm making this number up, of course, of 17% per hour. That's our goal, is to figure out K, the growth rate of this particular material. So simply plugging our numbers into our formula, okay, since Y is the final amount of material, obviously we let it sit for 6 hours, and at the end of the experiment, there were 6,000 milligrams in there. B, the beginning amount, of course, we ended up starting with 2,000 milligrams of material, times E to the, isn't K our unknown, right? We do not know the growth rate. That's what we're seeking to find. So K times, and then T, the amount of time it's been sitting, was, of course, 6 hours. So my formula ends up saying 6,000 equals 2,000 times E to the, we'll call that the 6K power. Okay, our job is to get K by itself. Well, aren't we solving an exponential equation? So if my goal is to get that K by itself to calculate the growth rate, since there's a dot connection, okay, let's do this as easy as possible. Wouldn't we divide both sides by 2,000? The 2,000s would cancel. Obviously, 6,000 divided by 2,000 gives us 3 equals E to the 6K power. Now, guys, go back to all those equations we practiced solving. If I'm ever looking for a missing exponent, I what? I log both sides. Remember, when in doubt, log it out. But because the base E is involved, we must use natural logarithms. Agreed? I'm going to natural log both sides. Whatever I do to one side, I do to the other. So if I ln both sides, I've got ln of 3 equals ln of E to the, okay, freeze. Why write 6K up here as an exponent when the rule for exponents was what? Always move them out front, in front of the log anyway, using the power rule for exponents. So the 6K, that exponent ends up dot connected in front of the ln of E. And you'll remember doing these from last, what, Wednesday and Thursday? ln E, if you ever see it, is really the number 1, isn't it? So it's ignored in this problem. I can divide by 6. The 6's cancel. And K equals, and then here's one of the reasons we always rounded our answers to 3 decimal places. If I push on my calculator, ln 3, hit enter, and then divided by 6, I get 0.183. Now don't write 0.183 and circle that as your answer. We wanted to know the growth rate. It's always written as a percentage. And of course, you remember from what, 7th grade math, to change a decimal to a percent, we move the decimal 2 to the right. Oh, so that stuff was growing at a rate of 18.3%. Of course, that'd be per hour, since the time frame was just in hours here. And that's how fast that particular material was growing. And really, when you think you got strep throat and they do a experiment or take a swab of a culture, a throat culture, so to speak, to see what's wrong with you, in essence, they're trying to see how fast this virus, this bacteria, this germ is growing. And the rate that it's growing is specific to that particular strand of whatever. And once they see the rate that it's growing, they know what it is that you've got and what antibiotic to prescribe to kill it and stop it from growing anymore, okay? So interesting how that works, and we had to use our skills that we learned this chapter in terms of solving an exponential equation, okay? All right, let's try a decay problem. Bottom half of my paper, we've got 17 years ago, Mr. DeMarco's hair weighed 275 milligrams. Now, his hair weighs 80 milligrams. So what's the rate of growth, or I called it decay, because obviously if his hair weighed 275 milligrams before, 17 years ago, and now it weighs 80 milligrams. Oh my goodness. What's the rate of the decay or the growth rate of Mr. DeMarco's hair? All right, so it's even, okay, you can just jot down little details that are important here. We're talking about 17 years passing, correct? We've got an original weight of 275 milligrams. We've got a weight now at the end of the experiment after 17 years of 80 milligrams. So again, we're trying to calculate that K value, the growth rate, or I called it what is the rate of decay, because of course we noticed the weight has gotten smaller, so it must be decaying rather than growing. All right, technically we're still finding a growth rate, and we're going to get a negative answer, I would think, right, if the material is getting smaller and smaller. So going back to our main formula, we've got everything we need to know, agreed. Y, the final amount of material, this hair currently weighs 80 milligrams. The beginning amount of material, back when he had a fuller head of hair was 275 milligrams. Times e to the, and then kt power, we're talking about 17 years, right? So 17k looks like our exponent. So dividing by 275, just like we did on that last problem. Again, pretty simple, straightforward calculation-wise in terms of solving the equation. Those will cancel. I'm going to go ahead and go to my calculator and push 80 divided by 275, giving me, looks like 0.2909, so 0.291, if I go to 3 decimal places, equals e to the 17k. Now don't say, oh gosh, I'm stuck now. No, you're not. You're looking for a missing exponent. So I'm going to log both sides. So the ln of 0.291 equals ln of e to the 17k power. That power goes out in front. And just like on the last problem, the ln e is irrelevant because it's really the number 1. So to get k by itself, I divide by 17. And it looks like we're going to end up with k equals, again, calculator. Don't try to type too much at once. One thought at a time here. We're going to go ln of 0.291, hit enter, then push divided by 17 and get negative 0.073. We were predicting a negative answer, correct? Because it was a decay situation. So it's growing at a negative rate since it's getting smaller and smaller. So technically we're going to go negative 7.3%. If you were labeling that, that's what? Per year, right? Rather than per hour. Oh, because that's how much hair has been lost in terms of over the last 17 years. So it's negative 7.3% growth rate per year on the hair. Okay? Let's make things a little tougher. You guys are advanced or honors. You don't want it to be too easy, right? Things that you can do that are a little different or less straightforward than what we just did. Look at this problem here. Let's look at the Louisville population. Now, these are made-up numbers. We're just trying to prove a point in terms of a mathematical procedure of how to calculate something here. The Louisville population, let's say 1995, was 5,685. And in 2004, after studying the progress of the population, it was 6,376. And if it fits the growth formula exponential scientific model that we've established, we want to predict, here's our question, if in 95 the population was 5,685 and in 2004 the population 6,376, when will the population reach 6,800 people? Oh, so we're now going to use this as a prediction tool to predict when the population will grow to end up being 6,800. So to do this, okay, let's think about what we've got here. Since we're starting with the year 1995, that's our initial population that we're dealing with. Do you agree that 5,685 is our beginning amount of people, and 9 years passes, correct? And we've got 6,376 people, That'll be our final amount. And the time that passed was 9 years. So we've got everything available to us other than the K value. So using those numbers, we can calculate our K value, correct? If we go to our formula, y equals b times e to the kt, y, my final amount, 6376, equals the beginning amount, which there were 5,685 people at the beginning of this experiment, times e to the, we don't know the K value, the rate that it was growing yet, but we do know that 9 years had passed, correct? So real quick, doing the same thing we did on the front of our paper, if I divide by 5685, divide by 5685, I'm now pushing 6376 divided by 5685, and I'm getting 1.122 on my calculator. So 1.122 equals e to the 9k. I'm going to natural log both sides, agreed? ln of 1.122 equals ln of e to the 9k. The 9k comes in front. We ignore the ln of e. Divide by 9, right? Just like we've been doing. And my K value is, now obviously the population was growing, wasn't it? There's more people in 2004 than there were in 95. So I'm predicting a positive answer here. I'm going to type in ln of 1.122, hit enter. Divide by 9, hit enter. And I'm getting 0.01279. Might as well make that as specific as we can. If I rounded that off to 3 places, it'd be what, 0.013, and that's no problem. I'm not going to get that specific on your final answers, but might as well get as specific a value as I can. If I move that 2 to the right, 1.279% per year is the population growth rate. Now, that's not my answer, because they didn't say figure out the growth rate. Oh, they said predict when will the population reach 6,800. So what do we do now? Well, think about it. We've got a growth formula now that says y equals, right? Isn't the beginning amount of people still that 5,685 value times e to the, well, we now know that the K, the growth rate, is that 0.01279 number that we just calculated, times T, and we don't know how much time is going to pass, do we, before we get to 6,800 people. But that 6,800 is the final amount of people we're seeking, so that's going to get plugged in for the Y, and we've got our K value, we just don't know our T value. Oh, so 6,800 equals 5,685 times e to the 0.01279 t. I'm going to divide by 5,685, giving me what? 6,800 divided by 5,685. I'm going to hit enter. I'm getting 1.196 equals e to the 0.01279 t. I'm going to ln both sides, right? ln of 1.196 equals ln of e to the, and then that power is going to go out in front of my ln of e. So I'm going to squeeze in 0.01279 t. The ln e is irrelevant, and to get t by itself, I'm going to, of course, divide by that decimal. So what am I typing into my calculator? I'm going to hit ln of 1.196. I'm going to hit enter, and I'm going to divide that by the decimal 0.01279, getting 13.99. So t is about 14 years. I'm not circling that though, am I? They didn't say how long was it going to take. They said when will the population reach 6,800? So it's going to take 14 years for that to happen. Oh, well, if our experiment started in 1995 and we're going to reach 6,800 14 years later, that's going to make the answer to our question finally, oh my goodness, when will the population reach 6,800? It should have happened in the year 2009. So you can use population growth models. It could be financial growth models to see when a certain stock's going to reach a certain number, but you can make predictions as to, when something's going to happen. Okay? And then finally, just to show you how you could set up something a little more challenging, if we go to my last question, I've got an experiment, and the population of flies is increasing at an exponential rate. So just a note, we've got an experiment. We were doing, in the experiment, the population of flies was being studied, and it's increasing exponentially. That simply is giving us the thumbs up to use our exponential growth model, okay? After 2 days, there were 100 flies present, and after 4 days, there's 300 flies present. So how many flies will there be after 5 days? Okay, now just to get you started on this, what in the world would you have to do to get going on something like this? After 2 days, we've got 100 flies. After 4 days, we've got 300 flies. So how many flies are there going to be 5 days later? Or I'm sorry, after a total of 5 days. Now notice what's different about this question. For the first time, what is unknown to us? We don't know the beginning amount of flies, do we? So isn't your common sense, your logical thoughts saying, I've got to do something here to figure out the amount of flies at the beginning of the question, which we don't know. It wasn't given to us. So watch this. I'm going to write y equals b times e to the kt as a reminder of that's my growth formula. And guys, look at this first scenario right here. After 2 days, so we know the time, there's 100 flies total. And then so we didn't know how many there were at the beginning of that situation, do we? We just know after 2 days there were 100. So 100's actually going to go in for y, the final amount of flies after 2 days. Equals, I don't know the beginning amount of flies, that's my unknown, times e to the kt. I don't know k, but I do know that what time? 2 days has passed, so that's 2k. Freeze right there. Couldn't I now go do the same thing with fact number 2 here? After 4 days, there were 300 flies. So I can put 300 in for the y, the total number of flies. 300 equals, I still don't know how many there were back at the beginning of this problem, do I? Times e to the, and now 4 days is passed, so my time is 4, and that would be 4k. So basically, I'm looking at two equations that both have unknown b values. So algebraically, if I told you, look guys, over here at equation 1, if I said, let's get that b all by itself, do you agree you would divide by the e to the 2k, divide by e to the 2k. Now hold on, I just caught myself making a mistake. After 2 days, there were 100 flies, not 200. So this should be 100, agreed? There we go. So we have 100 over e to the 2k is equal to b. Now what can I do? Think about it. If my b is 100 over e to the 2k, can I now take that expression, plug it into that b, in the other equation? So this would now say 300 equals, the b value is what? 100 over e to the 2k times the e to the 4k that's there. Now careful here, I'm going to cross cancel, aren't I? What's the rule? Hey guys, if I had x to the 7th over x to the 5th, I'm just making that up, and I told you to cross cancel, isn't your rule to get rid of the smallest exponent? Get rid of all 5 of those x's, and instead of 7 of them, there'd be how many? There'd be 2, wouldn't there? Because the rule was to subtract your exponents. So I'm going to get rid of this e to the 2k, and 4k is going to turn into what? Well, 4k minus 2k, I subtract my exponents, gives me 2k. So in essence, I have 300 equals 100 times e to the 2k. I, of course, to get this e by itself, could divide by the 100, giving me 3 equals e to the 2k. And then I could ln both sides, get ln of 3 equals ln of e to the 2k. The 2k comes out front. The ln e is ignored. I divide by 2, and my k value is ln 3 divided by 2. So on my calculator, I'm going to hit ln 3, enter, and then divided by 2, enter, and I'm getting 0.549 to the nearest 3 places. And now that I know my k value, couldn't I use that in my standard equation to actually plug it in where? Oh my goodness. Couldn't I plug that in right here? Right? And what would that do it would allow me to figure out the beginning amount of flies. And I'd have everything I need in this problem. So I would have 100 over e to the 2 times and then 0.549 power. And that little calculation on my calculator would allow me to solve for the beginning amount of flies. So for right now, instead of typing all that in at once, again, I'm going to push 2 times 0.549, hit enter, and that's what I'm going to raise e to. So I'm going to hit e raised to that answer that's on my screen, and then take 100 divided by that value. Now on my screen, I'm seeing 2.9998. So I might as well round that off to 3, agreed? This ends up being 100 over 3, which of course is 33.333. And that's my beginning value. This is my k value. Oh, so now I can try to predict, since I've got my k value and my b value, how many flies there are finally after 5 days. So I'd have y equals, the beginning amount is 33.3 times e to the what? 0.549 times, and then t, the amount of time is 5 days. I can type all that in my calculator and finally predict how many flies there are after 5 days. Wow. Thank God you're in advanced or honors math. You might want to rewatch that, or at least relook at your notes, or try that again before you'd attempt to do one like that on your own. Okay? So that's a pretty interesting day. Might as well do that real quick. If I did type that into my calculator, the first thing I'm going to do is hit 0.549. I'm going to times that by 5, hit enter, and I'm going to raise e to the number that's on my screen right now. So e raised to that answer gives me 15.56 blah, 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 times 33.333, hit enter, and 518.8, so 519 flies is the prediction of how many flies there's going to be in that room or on your lunch or wherever those flies are hanging around after 5 days, around that garbage, we'll call it that, okay? Now guys, your homework to try some of this exponential growth and decay stuff is attached as an extra worksheet on your Schoology. So look for the 421 worksheet attachment. Certainly just copy the problems down or print a copy of the attachment out. Give that a shot. That's probably our toughest assignment we've had in a while, which is okay. We got a much shorter, quicker, easier last thing to do tomorrow to wrap up this chapter. It deals with compound interest in the banking industry for those of you that are more financially motivated rather than science motivated. But again, today's Tuesday the 21st, so when you print out and try the 4 homework problems, they're due on the 22nd, on Wednesday the 22nd by noon, okay? Wow, thanks for hanging in there. Great job. Tomorrow is much, much shorter and straightforward. So if today was a 30-minute lesson, hopefully tomorrow's 15, and we're back to being what our average should be, about 20 minutes a day, okay? Thanks, guys. We'll see you tomorrow.